So in this lesson, we are going to talk about the minor monotonicity of the parameter mu, and I will just briefly outline what's going on about the proof. So first of all, we would like to examine what's the operation about this minor. What's it about this minor operation? So we call it as the minor operation because the smaller graph can be obtained by the bigger graph by the following operations. First, you can remove a vertex, you can remove an edge, you can contract an edge. But because you can remove any edges first, so you can remove all the edges first before you remove the vertex. So instead of saying removing arbitrary vertex, you can just say that you want to remove only the isolated vertexes, because you can remove the edges first and then remove the vertices. Same as the contracting an edge. In some case of the contraction, the two endpoints of the edge has the common neighbors. So in this case, you can just take out some of the neighbors and then assume that the two neighborhoods of the two endpoints of the edge are disjoint. So for contracting an edge, you can assume the picture looks like this. So to prove the minor monotonicity of mu, and we need the following lemmas. And basically, you just take care of each case one by one, then you are able to show the parameter mu is minor monotone. And these things are coming from the handout. And if we have time, we will give a proof. But let's go through the statement first. So the first one is the disjoint graph. This notation stands for the disjoint union of two graphs. Suppose G and H are two graphs, and then you do the disjoint union of that, then mu of this disjoint union is equal to the maximum of the mu G and the mu H. So that is to say, if you have these two parameters, then you are able to calculate the value of mu of G disjoint union with H. And in the particular case that when H is a K1, K1 we knew that in the previous lesson the mu of K1 is equal to m-1, which is 0. So mu G and mu K1, which is 0, the maximum of that is equal to mu G. And for the second case, when G and H are graphs such that H is a spanning supergraph. Here I call that as a spanning supergraph, means that G and H has the same set of vertices, and meanwhile H might have some extra edges that G does not have. Then in this case, we are able to prove that if G is a subgraph of H, then mu G is less than or equal to mu H. For this part, it requires some manifold theory and it requires the SAP that we mentioned before. But pretty much these two cases are easier to take care of. It probably just half to one page of the proof. But the more details is in the decontraction lemma. The decontraction lemma is basically saying the opposite operation of the contraction. So suppose that you have a graph G and you have an edge E, you want to do the contraction of that. Say G is a graph with an edge E, and UV are the two endpoints of the edge, such that the neighborhood of U and the neighborhood of V, taking out U and V themselves, these neighborhoods are disjoint. If this happens, then pretty much it looks like this picture. Then you can do the contraction. The contraction of G is less than or equal to the mu of G. So this one will take much longer proof, probably 1 or 2 pages. But all of them depends on the SAP. So let's move on to the definition of the SAP. A matrix, we only focus on the real symmetric matrix. A real symmetric matrix A has the strong Arnold property if x equal to 0 is the only solution to the following equations. So you will use matrix A to set up 3 equations, and then you will try to find the solution to these 3 equations. Suppose x equal to 0 is the only real symmetric matrix, the only solution to these 3 equations. Then it has the SAP. So you can just look at these as the equations, and in particular these 3 are linear equations with respect to the variable matrix x. For example, if ax equal to 0, ay equal to 0, then a times x plus y is also equal to 0. And ax equal to 0, a times 3x is also equal to 0. So these 3 equations are basically linear, and you are checking the set of linear equations and try to see if x equal to 0 is the only solution to these equations. So that's the first point of view. And the other point of view is that when you look at the a system of linear equations, the set of solutions is a subspace. So you can consider all the symmetric matrices. It is a vector space. Okay, and in this vector space, you have the origin, and then you can compute the first 2 equations together. These 2 will compose of a subspace. You can draw it like this. So this is a plane. It's a subspace. It's all the solution of ax equal to 0, ix equal to 0. And because the third one is also linear, so the solution to ax equal to 0 is also a subspace. So pretty much this condition is saying that the intersection of these 2 subspaces, the intersection of them only has the trivial intersection, which is the 0. And there are several examples that if you set up A equal to O1's matrix, then x has to be 0 from just the first condition. So A has the SAP. If you take A equal to O0 matrix, then x can be set up like this. When this lowercase a is, say, equal to 1, then ax is equal to 0 and x is not equal to 0. So A does not have the SAP. And moreover, here are more complicated, interesting examples. You can take A equal to the adjacency matrix of K13, B as the adjacency matrix of K14, and for the case of K13, if you want A circle x, I circle x to be 0, then basically x has to be look like this. I circle x tells you that the diagonal entries of x has to be 0. A circle x tells you that these entries has to be 0. So the only case is that x has to be a symmetric matrix such that there are some possibly non-zero variables happening on these entries. So when you calculate a times x, the regular multiplication, and it has to be 0, this condition tells you that a plus b equal to a plus c equal to b plus c. It has to be 0. When you solve these equations, then it turns out that a equal to b equal to c equal to 0, and x has to be 0. So through the computation, a has the SAP. But when you do the similar calculation, you will set up more variables, maybe a, b, c, d, e, f, and then you have 6 variables, and it turns out that you will find a non-zero solution to that. And in that case, you will find that B has no SAP. So in general, you will believe that if there are fewer variables, then it's easier to have the SAP. If you have more variables, then it's easier to lose the SAP, but that's not always true. If you take A as the adjacency matrix of Pn, the path, then you will realize it has a lot of variables, but it does has the SAP.